Buenos días, ¿cómo están? This is November 5th for the recording. And what I want to do is, per yester class's student request, I'm going to give you guys more practice first with, well, I'm going to let you guys decide. Do you want more practice first, or there's one more concept to add to the pile? We could do it in either order. So I'm going to give you practice with what is a radian, what is angular velocity, what does it measure, what does it feel like, blah, blah, blah. And then there's one more kind of acceleration that happens in circular motion. I can ask you guys, who wants extra practice first? Who wants the last equation? Concept, it's more than just an equation. Oh, hold them higher, I can't tell. Who wants the practice on the what is a radian, what is angular velocity first? That's more than half. Okay, we'll do that. But I'm gonna set my timer so that I don't forget, not forget, but get too engrossed. Okay, so welcome, bienvenidos, bienvenu, guten tag. We're gonna do some practice problems. Let me see if you got the foundation, beginning, itsy bitsy bit. Put this in the Google form, and what? Put this in the Google form, A, B, C, D, and this will show whether we can start here or if we need to review the basics. Ready, set, go. You may use your notes. Question. Sure. Not big enough? Bigger anyway. I mean, the degree symbol is good. The degree symbol is great, but yeah, DEG. Oh, perfectly set. So far, so good. So far, so muy bien. One minute, and show me what you got. I think that we can move on. Mostly move on. Hey, by the way, hint for letter D, 150 meters is really big. And a pie that's 5 centimeters wide is not really big. I encourage you to think about magnitudes and common sense and get a feeling for just how big a meter is and what 150 meters would look like. Okay? And if you got 150 meters, you made a mistake. And you got like 30 more seconds. See if you could fix your mistake. And I'm going to call that time. 5 minutes to do 4 questions should be enough at this point. So let's do them. I am very pleased. The vast majority got A and B right. Whoa, here we go. A vast majority got A and B right. Well, more than 2/3 got C right. D, not so much, not so much. Let's talk about the arc length formula. Amar, there is a survey on the Canvas page for the SI session. If you go to My ASU, click on 111 and click on the SI Canvas shell, there's a survey on it. If 80% of the class does that survey, you'll get up to a bunch of extra credit. Okay, so las respuestas correctas, 290 odd degrees. Actually, I should round that to 300. There's only one sig fig. Whatever. 286, 290. 0.2 his hertz. Angular frequency 31.4. I should really say 31. And 2.6 centimeters. Okay, now how do we get this? How do we get this? Degrees to radians conversion. 5 radians times how many degrees in 1 radian? I think of this as 1 degree equals 57.3 degrees. Did I just say that backwards? 1 radian equals 57.3 degrees. If I multiply radians over radians, units cancel, and I get 290. The relationship between frequency and period, frequency is 1 divided by period, and vice versa. So 1 divided by 5 equals, big shocker, 0.2. The relationship between F and omega is hertz, means cycles per second, or things that happen per each unit of time, whereas radians per second, not radians per second, radians per cycle, if I want to convert from cycles, full circles to radians, I'd use the idea that there are 2 pi radians in a full revolution. I've got something with an angular velocity. 5 times 2 pi is 10 pi, or about 3.14, 31.4, whatever. And finally, there is the formula that you should have, S equals R theta, but 5 times 30, 150, is not the size of a pie crust. What's the goof there? Radians, baby! Radian it up! It is not 30 degrees, it is 5 centimeters times 30 degrees times 1 degree, 1 radian over 57.3 degrees. We have to convert. The formula does not work if you just multiply degrees by radius. You have to cancel out your degrees, cancel out the degrees, divide by 57.3. And again, the correct answer is about 2.6-ish centimeters. Take a look over this, especially the last one. Thou shalt use radians in just about all the formulas. Anytime we have an angle, convert to radians. That's our standard unit. Unless I specifically ask for degrees as the output. Except for the last one, which is understandable novice goof, not showing a serious lack of understanding. You've got a formula, just misapplied units or misunderstood the nature of those units. I think this looks pretty good. Let me take questions first about anything in the lecture that I said last time. No, 30 degrees of pi is not a full pi. That'd be 360 degrees. You could use 360 degrees. You could use 360 degrees. You could use 2 pi radians if I said, what is the full length of the pi crust? What is the length of an entire pi crust? But if I'm giving you an angle here, I'm saying I've got a slice of pi. Could have said maybe in words there, a slice of pi. If you found the entire length around using 2 pi r, okay, just learn here if I'm giving you an angle here, I'm talking not just about the entire pi crust, but about a slice. Yeah.
So you give us the radius and the degree for the angle. We essentially got to do we got to convert the angles from that to radians.
That's what this is.
So always.
Always, if you want arc length to work, thou shalt convert thine angles to radians. That formula does not work with degrees. S equals r times theta, it only works with radians. Yeah, please. 180 over pi, yeah. If you want precision, infinite precision. It is the idea that 360 degrees and 2 pi radians are the same number. So conversion 360 over 2 pi or 180 over pi is that. Other questions? Okay, how about a homework example? I had a couple of students ask, one on email, one on office hours, about some homework questions. And I think that it might behoove us to hit on one of them. In particular, the nature of graphs and how to read a graph and how to deduce motion and deduce properties of a graph. So let me do a homework problem for you, or part of a homework problem, or guide you to a homework problem. Give you the puzzle pieces, or hopefully not give, hopefully refresh you on the knowledge that you should hopefully remember before. If I have the idea that velocity is defined by the equation, change in x over change in t, what does that look like on a position time graph? If I've got x on the vertical axis and t on the horizontal axis, how do I find velocity of that? Slope, exactly. Slope is the velocity. Oh, let's do an example. I'm going to give you the function. Let's make sure you know how to do this. I'm going to give you the function position as a function of time equals 5 meters plus, let me make it bigger so that people can actually see the sucker. Oh, for God's sake. I'm going to give you a function. Position as a function of time equals 5 meters plus 8 meters per second times time. 5 plus 8t. Google question E. Find velocity. I should actually properly say that's a vector. Hmm. 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 Okay, so I need to remind the class of this. If I have the equation something y equals constant plus constant times independent variable, what those puzzle pieces mean are the x-intercept and the slope mean at the vertical intercept, that is to say when time is 0, this shows where you are. I would call that your initial position. This is x initial. And this term here, whatever multiplies t, tells you as each second goes by, how does x change? If run is 1, if t advances by 1, how much does x advance by? Google Form E. If t goes up by 1, how much does x go up by? This is a bigly hint. One more time, the big hint on how to find velocity out of an equation is to reason about velocity as how much does position change as time changes. So if time goes up by 1, can you tell me how much does x change by? This is E, not F. Okay, so many people were able to deduce that if t gets 1 unit bigger, I am adding one more multiple of 8. The rise when run is 1, the rise over the run, the slope, the velocity is what is multiplying t. 8 meters per second was the correct answer. Oh, maybe that was unfamiliar. Let's find another way to do this. What if I gave you positions at various times? What if I tell you that x initial equals, let me tell you, points on the graph, let's say. I'm going to tell you that I start here, then there, then there, then there. This is a different problem here. I'm going to say at time 1, come on, the coordinates at time 1, x equals, usually I do the horizontal coordinate first. Time equals 1 second and x equals, I don't know, 3 meters. Then at time equals 5 seconds, whatever, 3 marks, 3 seconds, then x equals 6 meters. Sure, why not? Find velocity if I tell you the velocity and time at distinct points. This is Google question F. In this example, what is the slope of this line? I go from 1 comma 3 to 3 comma 6. Show me how much you remember about first module. Google question F, find the velocity. I've given you everything you need to plug into a formula. Blast it. What are the units, by the way, of velocity? How do we measure miles per hour in SI units? Hint, hint. Okay, 1 minute. That's enough people getting this right. Okay, so you correctly deduced that if rise here is 3 meters, 3 to 6 is a change of 3, and run is a change in time of 2 seconds, the rise over the run is 3 meters divided by 2 seconds, 1.5 meters per second. Check. Let's change this problem now. Instead of talking about velocity and position, I'm going to ask you about if I've got angular velocity, that tells me how angle is changing as time passes. Let me give you a graph. I'm going to go from, this is a graph of theta in radians versus time in seconds. I'm going to go from at time 0, I'm at, I don't know, 5 pi radians. And it takes me 10 seconds to descend to 0 pi radians. Yeah. Well, let's see if we can do this much. Let's start simple. Find omega. And I should properly be saying, in this formula, angle has a sign. I don't just have to say speed. I could say angular velocity. Tell me with the sign. This is Google Form G. Google Form G, find the slope now. Okay, now this is proving harder. Much harder. Okay, so we've got about 90% of you here. Let's apply the formula here that we've got. 90% wrong. Let's apply the formula we've got. Step 1, what is the change in theta if I go from 5 pi radians to 0 radians? Google Form H. Let's build this up piece by piece and see where you're falling apart. Find delta theta in this, between these 2 points. Again, this is H. You could tell it's question H because I put a big H in front of it. Don't put this in I, please. This is H. H, H, H. What the H are you doing? Okay, 1 minute. Not where I want you to be. Okay, so I want to take a look at the y coordinate, the theta coordinate that I gave here. This is not the number 5. This is not the number 5. This is 5 pi. In other words, 2.5 turns, 2.5 revolutions. 5 pi is not 5. Pi, even in Indiana, is not 1. Pi is roughly 3.14. 5 pi is about 15.7. So please don't ignore the existence of one of the most important mathematical constants ever. Final minus initial, delta theta, equals theta final minus theta initial, equals my final, I am going to pick the later time, minus the initial time, 0 minus 5 pi, equals negative 5 pi, or equivalently, you could say negative 15.7-ish, and I should say radians to be precise. All right, so don't forget what a change is, or what that pi is just a number, approximately equal to 3.14-ish. Let's do another example of this part to find a change here. I'm going to give you a different, let me change things up a little bit. I'm going to say before I start my stopwatch at time -2 seconds, my angle was what? What should my angle be? 12 radians. And then some later time, 15 seconds after I start my stopwatch, my angle is -1 radian. Again, find omega. This is Google question I. All you have to do is subtract here. Again, I'm going to ask you to find the change in angle between these two times. And there's a Google question. Can I show the full page? Oh, we already answered this. So by the way, if a question asked is the 12 in degrees or radians. If I give you a number for an angle without specifying, it is always assumed to be the SI standard, the radian. Always. If I don't specify, and if I don't specify the format I want it in, it is always assumed to be in SI standard. You should always default to giving me meters, kilograms, seconds, radians, so on. Okay, let me strongly encourage you, by the way, again, look at here, final minus initial. And note the numbers. Is there a pi on the board right now? Is the pi in the room with you right now? Okay, to solve this, I'm going to use final minus initial. Theta final minus theta initial equals -1 minus 12. The rumor has it as -13 radians. Most got that, but I'd like this to be all. This should not be the breaking point. Let's check further. though, can you plug into the formula? Find me omega. So the Google question J, find me omega. Please note, here I am talking about angular velocity. So angular velocity, slope can be negative. That's why I've written all these decorators on top. Okay, well, no, this is an important, good question. We'll discuss this in a second. I've got someone asking what it means, and we'll want to hit that. And I'm going to call that times up. The correct answer is about -3/4 of a radian per second, -0.76 whatever radians per second. All we do is we divide the change in theta, -13, by the change in time, 17, -13/17, 0.76, whatever, -0.76. Now, I had an outstanding question, something that gives me great hope, is what does this mean? Can you explain this critically? What is the angle of a straight line? Let me answer the second part first. I'm not talking about the slope of this line being an angle. Yeah, you could pretend this is a hypotenuse of a triangle. No, 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 no. This is a graph. This is not a diagram. There is no such thing as the angle on a graph here. If we're graphing theta versus t, we're not talking about comparable things. It's not a picture. So there is no angle to this line. Rather, what this graph is talking about. Look at the vertical axis. Identify what this symbol means. Theta is the angle. I am talking about where something is pointing as time progresses. This says that, I guess, 2 seconds before I start my stopwatch, 2 seconds before t equals 0, something is at an angle of 12 radians with respect to whatever we've called the origin. Maybe this is I don't know, a kid is playing with a yo-yo, and the yo-yo string is originally wound 12 radians worth of angle. What is that? Something roughly kind of like 2 full circles. Oh, that's not a very long yo-yo string. Whatever, doesn't matter. So we've got a yo-yo or something that is wound 12 radians worth of angle, and that yo-yo is presumably unrolling. We've got a rotation. Theta is changing as time progresses, and then sometime later, 15 seconds after I hit the stopwatch, 17 seconds after this instant, I'm saying that the yo-yo is rotated to an angle of -1 radian, 1 radian clockwise from wherever we say 0 is. Maybe it's bouncing back and starting to roll back up the string. So again, what does this represent? I am not talking about an angle of this line. Slope is not an angle of a line. Slope is the relationship between the y-coordinate, the vertical coordinate, and the horizontal coordinate. It tells me how rapidly this changes as that changes. The ratio of their changes is the meaning of slope. So what is the angle in a straight line? The angle here is not talking about the angle of the line. The angle is the y vertical coordinate at each instant. I hope that that clarifies a little bit about how to interpret the graph of theta in this case. Okay, I think that I get enough right answers. Well, more than half of the class is getting this right. Let's talk about the graph in the homework and identify this. This I'm not having you calculate. This in the homework question 2, I think. I don't have you calculate numbers. which is good because you would need calculus to calculate some of these functions explicitly. Rather, what I'm having you do is identify qualitatively if theta is changing smoothly, how does an x position change? How does a y velocity change, or whatever? In the homework, I ask a question about a wheel which is spinning. Let's say I've got a dot on a wheel. I take a wheel, I mark some point, put a piece of paint or tape on the top of the wheel, and I spin it around the axle. So this is not rolling, by the way. Wheel is stationary. I'm just spinning it around the axle, spinning it counterclockwise. Let's analyze everything we can about this. Sketch the shape of positions and velocities and angular velocities and angle as time progresses. This I can't have you do on the Google form, as these are graphs. So this is on your honor. You are going to work with your classmates. I want you to try to sketch the following graphs as best you can. Tell me the angle versus time. What is happening with the angle? I'm going to define, by the way, the coordinate origin is xy equals the normal. Horizontal is x, y is vertical, math standard. And I'm also going to define that the angles are measured counterclockwise from x, like I said, is the math standard. Okay, so I want you to talk to me about theta. I want you to talk to me about omega. And why don't you see if you could tell me where horizontally the object is and where vertically the object is as time progresses. Again, the object is just a little piece of tape stuck to a oh, for God's sake, my words, it's so hard today. A little piece of tape stuck to a wheel that you're just spinning. Give this a shot and please work with your neighbor. The standard convention is yes, clockwise is the negative direction. Here's an increasing angle. Theta is 30, 40, 50, 60. Negative angles are that way. Google question K. Tell me when you're roughly got a best stab at it. Because I can't hear how many people are done. Daisy? Sketch these 4 graphs or attempt these 4 graphs. And then Google question K, tell me when you've made your good old college try with it. Yummy? I want you to find out as much as you can, try to get at least a qualitative sketch of what angle is doing as time progresses, what omega is doing as time progresses. You don't have numbers here, but I don't ask you to do numerical calculations for this question in the homework. What is the shape associated with this behavior? So again, question K is tell me when you're mostly done. And then I shall explain in gory detail.
Like they should be. Yeah, yeah, no, they should be. Oh, no, no. Data's different. Well, like, change, that would be, how deep through it, just like that. So I don't need to do that part? Oh, so I didn't get to draw that. Oh, okay.
Okay, two more people and I will show you the way. Great, let's do it. First off, if we've got a wheel spinning in uniform circular motion, please note everything I'm talking about, we are moving smoothly. We have not talked about what happens if the spin rate changes. That's actually, I'm going to call that beyond the scope of what we're doing here this year. So an angular acceleration, I'll announce in a minute, is not going to be tested upon at least. I'll only mention it in the homework. Tell you about that in a second. So, if omega is steady, then I would say a horizontal graph should have the same omega value as time progresses. Is omega positive, negative, or zero here? Negative. Clockwise is the negative rotational direction. It's our convention. There's your graph of omega versus time. Oh, I like to decorate things. Okay, now, what is the relationship between omega and theta? Omega is the slope of theta. So the slope of omega is 0, so theta is 0, right? No, listen carefully. Omega is the slope of theta, not theta is the slope of omega. If omega has a steady negative value, that says theta has a steady what? Omega is the slope of theta. If omega is constant negative, the slope of theta is constant negative. Slope of theta is negative constant. Okay, now, one more thing that we can deduce about this. What's the initial value of theta? I'd say the initial value of theta, this is one thing I can tell you precisely, is pi over 2, 1.57-ish. How did I know that? Because I measure angles relative to the x-axis. I drew this at the furthest y extent. Okay. No questions. For reals. I didn't give you enough to deduce any other number, but the angular position at time 0 is the one and only thing that I think you can deduce from the sketch. Moving on. Okay, now let's talk about x and y. Here's a new thing. We are just looking at where an object is as time progresses. We are looking at it in one dimension at a time. You have to succeed in problem 2 on the homework and a related quiz exam question ideas, you have to identify what is happening in the direction chosen. So if I am talking about x, you have to ignore up-down motion. You have to ignore up-down position. Simply say, where am I? Left, right. Where am I on the x-axis? If the origin is the axle, I start above the origin. I start above the origin. I start vertically above the origin. What's my initial x value? Google form. If I start above the origin, if I start at a positive y value, what's my x? Google form L. What is my initial x? Again, my initial position is right there, directly above the origin. Tell me about where it is horizontally. Okay, the general consensus is that if something is up is not left, up is not right, up is up. Up is vertically above the origin, means your x equals 0. Think of a graph of x comma y. What's the y coordinate for that? What's the x coordinate for anything on the vertical axis? It's 0. So at this time shown, x is passing through 0. What's going to happen a millisecond later? I'm going to go there, and then I'm going to go there, and then I'm going to go there. What am I doing? What is my position doing? Google Form M, what should my graph do? What is happening to my x value? I start at 0. Now what is happening to my horizontal position? Does it stay the same? Does it get bigger? Does it smaller? Does it jump to a different value? What can I say if my x starts here at time 0 and then 1 millisecond, 2 milliseconds, 3 milliseconds? How am I proceeding x-ward? The piece of tape is rotating around with it. Is it changing? How is its horizontal coordinate changing? I see positions 0, 1, 2, and 3 moving rightward. Right is usually associated with the positive direction, so I say my x increases. But hold on a second, I am not moving along a straight line. What happens as x gets here, 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 here much later? If I am going downward, how much am I moving rightward? So that should be a bigger question. Google N. What is my left-right motion in those 4 points? Am I moving left-right? Am I moving fast or am I moving slow over those points? In particular, as I approach the right edge of my motion, what would the value of my position be? Is the value of my position. What happens to my position? Wait, hold on. I changed the question. What is my velocity? What is my velocity? What is happening to the slope of my position graph? I think that I am moving downward, and downward motion is not left and it is not right. Vertical motion is not horizontal. So I think my position graph has to taper off. I have no slope at the instant when I hit my maximum rightward position. Then I keep going around. Which direction am I going now horizontally? Left. So what does that mean on an x-graph? If my direction of motion is leftward, how do I see that on an x-graph? I am decreasing leftward motion, negative displacement. I actually want to make this tighter graph. I decrease. At some instant, I pass back through the origin, my x origin. I'm passing directly below the origin, so I hit this point again, and then I go negative. and then I go positive. Oh my God, it's the sine function. And then it goes up, and then it goes down, and then it goes up, and then it goes down. The x increases and decreases and increases and decreases along this path. On the contrary, my y coordinate starts at its maximum, passes through 0, passes through negative, passes through maximum, so on and so forth. I start at a high place, go through my vertical origin, y equals 0 here, then go to a low place below the horizontal, below the y equals 0 level. I am below the coordinate origin. That's down here, and then I keep rising and going up and down. Here are how to find x and y graphs. I don't ask you exactly this question, but if you can reason through, make a little dot and say, all right, how is my x changing? Where am I left, right? Am I going left, right? Or am I staying at the same place, roughly left, right? I will leave it to you to do no, I will not leave it to you to do the velocities. Here's how to do the velocity. Look at the slope, the rise over run at any given little instant. Let's specifically zoom in on the x graph here. What is happening with the slope initially? Let me draw in a different color here. What is happening with the slope initially? What is the initial value of the slope here? Positive, negative, 0, big, small? Positive, big. Okay, I start out with a big slope. Then what's happening? Is my slope getting bigger or smaller? Look at the rise over run. Look at the rise over run here. How much am I rising and how much am I running? You can zoom in on individual points perhaps. Here's an equal amount of run. I think I rise a lot here, a little here, and very little there. My slope is still positive or negative? Positive slope, but decreasing slope. What happens at this instant? Am I rising or am I falling at that instant? Slope is 0. My slope passes through 0. My slope goes negative, negativer, negativer, negativer. Less negative, less negative, less negative, less negative, passes back through 0 and so forth and so on. Look at each little part of a graph and say, how is the slope at these points progressing? And I think it might actually be useful what I just did that seemed to make a click, at least for, I think it was Yami, said out loud, I heard, is you can draw point pairs on the graph, identify what's the slope just between those points. If they're near together, the slope around that region is the slope between those points, roughly. Slope there to there. Hey, that's the slope roughly of that, slope roughly of that. Oh, I'm getting steeper negative, larger negative velocity in that direction. Okay, on to the last idea in this module, this topic, I should say. 111, fall 25, slide set 4. Okay, so here's the big EO idea, EO. What's velocity? Not just the slope of position. Velocity has dose parts, speed and direction. And a big thing that we did once upon a time is we talked about how speeding up and slowing down are still physics acceleration. We say two separate things in English. We talk about speeding up, accelerating, slowing down, decelerating, but to a physicist, those are the same thing, differ only in the direction of acceleration. Speeding up is accelerating in the direction of your velocity. Slowing down is accelerating in the opposite direction of your velocity. Deja vu? Yeah? Direction does not just have to be straight forward and straight backward. You can turn from heading northward and not just turn straight around and go southward, right? I once upon a time turned from going westward to going northward. Go me, right? That's an acceleration too. That is not an acceleration in the direction of motion. That is not an acceleration in the opposite of the direction of motion. to accelerate from westward to northward, I had to accelerate perpendicular to my motion. Not parallel, not anti-parallel, but perpendicular. Velocity is speed and direction. If I change the direction, that's still a form of acceleration. To a physicist, there are 3 accelerators in a car. The gas pedal is an accelerator, the brake is an accelerator, and the goddamn steering wheel is an accelerator because it changes your velocity. Not your speed, but the direction of motion. I claim that if you move in any circular path, if you are doing wheelies, no, if you're doing donuts, or if you're just turning, if your wheel is not straight, then you are accelerating. And this is called centripetal acceleration. I also call this radial acceleration because the acceleration direction is in the same direction as a radius line. The direction of the acceleration is into the turn, and the magnitude, I give you a formula here. This is not an or symbol, this is division, v squared divided by r, fraction, or r times omega squared, okay? Magnitude is easy peasy, right? I give you a formula you should be able to plug in. I'll ask you to do this a bunch of times. You okay with this? I think the harder part here is the direction. Let me ask you this. If I want to turn right, do I turn my steering wheel toward right or toward left? If I want to turn right, which direction do I turn my steering wheel? That's the direction you are accelerating when you are turning right. Is that toward the center of the circle you make or away from the center of the circle you make? If I'm turning right, am I turning toward the center of the circle or away from the center of the circle? Toward the center of the circle. The center of the circle I'm making is on my right. I turn the wheel to the right, yeah? The direction of the change in velocity, therefore the direction of the acceleration, is in towards the center of your circular path. So we've got a clock right there. Half a second. We've got a clock right there. The second hand has a bug on the top of it. When the bug is passing the 12 o'clock mark, the bug is moving rightward. As the bug goes to the, I guess, second hand would be the 5-second mark, it is going a little bit downward and rightward. As the bug keeps going on, they're going more down and less right. Yeah, you visualize that? Okay, I ask you this. Is the bug accelerating towards the clock center or away from the clock center? When you're on top, you go right, and then you pick up a velocity that is more down. If you're on top of the origin and then pick up a velocity that goes downward, well, I think that's towards the origin. Yeah? Okay with that? Question? Nope. If you're going left, you're above the origin, going left and down. Down is towards the origin. Or if you're on the bottom of the clock, if you're at 30 seconds past and you're going, first you're going left, then you're starting to pick up an upward motion as you're going around the clock. Left, upward from the bottom is still towards the center of the clock. There is a huge point of confusion that many people have, which is, if you are turning right, what's the direction of the force on you? Aren't you flung towards the left wall? Right? Everyone feels flung towards the left wall, the outside of the turn. We call this centrifugal force, and it's a lie, baby. There is no leftward force. When we're in a car that is gunning it forward, do you feel pressed backward? No, you feel the seat moving forward into your back. The car is accelerating around you. There is no force pushing you backward. There is a force pushing you forward. It is the seat back pushing you forward as you need if you're going to accelerate forward. If you're going to stay with the car, you need a forward force to get a forward acceleration. Yeah? There's no backward force. It's the fact that we think of the car as stationary that makes us think you're being flung back. You're not being flung back. You're moving forward. You're moving forward because of the car. The car moves into your back, pushes you along with it. Likewise, if a car turns right, if you did not experience a force from the car, you go straight, right? If there were no car that you're in contact with, Newton's first law, you would have to go straight. The car turns around you. If you're going straight and the car is turning right, which side of the car do you touch? The car's left side runs into you, yeah? This needs a picture. Why have I been saying this? I need to picture this. Here. If you are in a car and the car is turning, if I were not attached to the car, I would exit the left side of the car, or rather, the car's left side would pass me, yeah? I'm not flung left. I'm trying to go in a straight line. The car's left side is pushing me rightward. Force really is inward. Hold on 1 second, y'all. So the direction of the acceleration in circular motion is towards the center of the turn. That means that the force is towards the center of the turn. In order to experience an acceleration, you have to have a force in the same direction. By Newton's second law, F equals ma. If you can calculate F, you can calculate A. The last thing, nope, I have cut this out of class. I need to emphasize one thing that you need. I need to emphasize two things that you need. G is 9.8. If I ask you to measure things in terms of G, I would say, 19.6 meters per second squared is 2 Gs, because it's 2 times as much as 9.8. If you calculate acceleration in meters per second squared, and you divide that by 9.8 meters per second squared, that gives you acceleration measured in multiples of G. Okay? When you hear someone saying, this plane pulled 17 Gs, haha, no it didn't, it would break apart. This plane tried to pull 17 Gs, that means it is accelerating at roughly 170 meters per second squared. No, it doesn't, it breaks. Okay. The last thing is, for our class, there is no change in speed in a circle. That's called tangential or angular acceleration, and it's 0 for us. There is no tangential or angular acceleration as long as you're moving in uniform motion. If you know that, I do believe you can do every homework problem and the quiz. Sorry that went to the end. I love you. See you next week. I'm going to lead with that. Hold on, wait, let me hit stop.